Again, welcome to Python programming language course. In this lectures, we're going to cover the linked list data structure. So we are going to again cover a data structure course using the Python language. These lectures cover chapter 18 of our course textbook. So our main objective is to design and also implement a linked list. We're also going to explore variations of linked lists such as circular lists and also double linked lists and simple linked lists. So 3 types of linked lists. We're also going to discuss about the concept of iterators. Iterators are used in object-oriented programming to transverse elements in a container. So first we start with the definition. What is a data structure? In a very one sentences, I would say a data structure is how data is organized in a program and the operations we can use to manipulate the data. So here we say a data structure is a collection of data organized in some function. Also, a data structure not only store the data, but also support the operations for manipulating data in a structure. So for example, an array is a data structure, which holds a collection of data in sequential order. You can find the size of an array. We can store, retrieve, and modify data in an array. But array is a simple and easy to use, but it has 2 limitations. Again, we already cover array. Array is the same as list in Python. So the limitation of a list or arrays is that once an array is created, its size cannot be altered. So an array is a static data structure. We always have to specify the size of the array. And when it's created, we cannot change the size during the execution of the program. We can only change the size when the program is not executing. Yes. Now also, array provide inadequate support for inserting, deleting, sorting, and searching operations. Now, next we talk about object-oriented data structure. Here we say in terms of object-oriented thinking, a data structure is an object that stores other objects. So example, a linked list is a data structure. It's an object that stores other objects. This is referred to as a data or element. So some people refer a data structure as a container object or a collection object. Now, to define a data structure is essentially to declare a class. So now if I'm going to create a linked list, data structure have to declare a linked list class. If I want to create a stack data structure, I need to, again, declare stack class. So the class for the data structure should use data fields to store data and also to provide method to support the operation, such as insertion and deletion. So in linked list, we have a method to insert an item into a linked list, a method to remove an item from a linked list. Now, to create a data structure is therefore to create an instance from the class, which will be the object. In object-oriented programming, when we have a class, to create an object of a class, we say the instantiation. So you can then apply the methods on the instance to manipulate the data structure, such as inserting an element to the data structure or deleting an element from the data structure. So we have 4 classic data structures. In these lectures, we are going to cover the list. In our next lectures, we're going to cover stack, queue, and priority queue. So here we say a list is a collection of data stored sequentially. It supports insertion and deletion anywhere in the list. And also a stack can be perceived as a special type of a list where the insertion and deletion take place only at one end. Normally we refer it as the top of the stack. So from the top of the stack, we can push an item into a stack. We can pop an item from the stack. We can check what is on top of the stack. And we can also check if the stack is empty. Also, a queue represents a waiting list. So where insertion takes place at the back, also referred to as the tail of a queue, and the deletion takes place from the front, also referred to as the head of a queue. So stack is last in, first out. We can push an item from the top we pop an item also from the top. So that means if the first item I put in the stack will be the last item to come out. But in terms of queue, we have two. We have different place we insert an item, different place we remove an item. So queue is first in, first out. We insert an item from the tail, and then we'll remove an item from a queue from the head. Or we can use the term front and the rear or back. So a list is a popular data structure to store data in sequential order. So for example, a list of students or a list of available rooms or a list of cities can be stored using list. Now the common operations of a list can be, we can retrieve an element from the list. We can insert a new element to the list. We can also delete an element from the list. Also, we can check how many elements are in this list, which will be the size of the list. Also, we can find out if there's a specific element in the list. So this would be a search method. Also, we can check if a list is empty. So linked list also is a list of items called the nodes. So a linked list consists of nodes. The order of the nodes are determined by the address called the link stored in each node. Here we're going to use the term nest as the link. So every node except the last node will contain the address of the next node. So the component of a node is two things. A node may have the data part. This is where information is stored. And the link will be the address of the next node. So the next node will be pointing where the node is pointing to will be the address of that node. So we have some few terms here. What is a head or first? A head or first is a special node that point to the first node. So here we'll say that the head or first hold the address of the first node. Since it points to the first node, it's going to hold the address of the first node in the list. Now the info part, or we can say the element on the node, can be either a value of a primitive type, or it can be a reference to an object. So we may have a class name node, which represent node on a list, and it has two instant variables. The element, which will be where the information will be at, and also we have the nest, which will tell us the address of the next node. So this is an example of a linked list. Consists of element or node 1 up to node n. So we can see the special node called the head. It points to the first node. So that means the head node hold the address of the first node or store the address of the first node. Now the first node is pointing to the second node. So that means the next section is the address of the second node. And the element 1 will be the information that we are storing. As we said earlier, the information can be a primitive type, or it can be a reference, also a job object. So the last node always will point to null because it's not pointing to any address. And we call the last node as a tail node. So this is a Python syntax. We start with a keyword class. As we said, again, data structure use object-oriented concept. So the node, we create a class node, and we have our special method to initialize. And then we have two elements. So the element and then the nest. Here we assign none to the nest because it's not pointing to any address yet. And the element will be the data or the information for that node. So again, that's the syntax for Python creating the class node. Now we want to add 3 nodes. First, we need 2 variables here, the head and the tail. So we assign the head none, the tail none. Remember, the head is a special node that points to the first node. The tail is the last node that will point to null. Now this means if I have head assigned to null assigned to head and none assigned to tail, it means what? The list is empty. They are not pointing to anything. Now we had 3 nodes. The step 2, we create our first node. Again, linked list is a dynamic implementation. So the size doesn't matter. Anytime we want to set an item, we need to create the node first before we insert it. So the first step is create the first node and insert it into the list. So here we use the node class constructor. So node, the node will have a string, Chicago. We assign it to the head. And also we assign head to last because it's only one. So this is what we're going to have. The tail also point to the first node because we have only one node in the linked list. So both the head and the tail point to one node. And the content is Chicago based on the constructor of the node. We initialize the object node with constructor Chicago. The next, we are going to create our second node. So our second node, we use the node constructor again, and we are going to have Denver. So now Denver, we are not going to assign Denver to the head no more, but rather the tail. Why? Because the head is already have its node Chicago. Now, if we assign to only tail, that means it will stay in the same position. So we say tail.next so that we move to the next node. Then we assign the tail.next to tail because that's the last node. So again, we construct our second node, Denver, using the constructor for node. Then we assign it to tail.next because we have to move. We use next to move to next memory space that will be allocated dynamically. So this Denver memory space allocated dynamically. So right now, the first node have the address of the second node. Then we don't want the tail to stay at the first node. You have to go to the second node. So we assign tail.next to tail so that we move the tail to the next node. Then the last one, the third node, is called Dallas with the constructor again. After that, we move the tail one more time. So we assign tail.next to tail. And that will be the final diagram here. Now to transverse all the elements in a linked list, we can use the pointer, but let's look at this diagram first. Now, when we look at this diagram, if I want to transverse through these 3 nodes and I use the head pointer to move, what will happen? If the head pointer moves to the second node, which is Denver, the first node will be dereferenced. It's not going to reference to anything. So it will be wasted, removed from the linked list. So because of that, the first thing we do, we create a second pointer. Now you can name the second pointer any name you want to. Here we name it head. So we assign head to current. Now we use the current to move through. So we say why current not equal to none, which means we haven't reached. Remember the last node address is none. We haven't reached the end of the linked list. We're going to print current.element. So we are printing the element. When we print, we move the current to the next node. So we have current.next assigned to current. So here we say that each node contains the element and also the data feed name next that point to the next element, which will be the address. Now if the node is in the last in the list, then its pointer data feed next contains a value none. So here we can use this property to detect the last node. Excuse me. So here none becomes like a sentinel value for while loop. While the pointer current has not reached the none, we are going to print each element and move to the next. So for example, you may write the following loop to transverse all the nodes in the list. Why? First of all, we create a pointer. If we use the original pointer, we are going to lose all the items. When the pointer moves to the next node, we lose the previous node. So we create a new pointer and we use that pointer to move through all the elements. Now let's look at the linked list class. So as we said, a linked list consists of nodes. So we can see that we have the node class here. And this node class doesn't need to have a behavior because linked list is going to use it. So the node have only 2 parts, the element section and the address section. The address type is always the node type. Now we have our linked list. Our linked list here, so we have our head. Remember, the first node is head, so we assign the type is node. The last node will be tail. We need a variable, so we assign. Then this is an option. Here we have a variable size that will tell us how many node we have in the linked list. So anytime we insert a new node, we increment the size by 1. Anytime we remove an item from the linked list, we decrement the size by 1. So next we have the linked list constructor, default constructor. Here we say create an empty linked list, the constructor. Then next we have a hard first. Hard first, we insert a new node into the beginning or the head of the linked list. So here we say add a new element to the head of the list, but hard last will add node to the end of the linked list. So it will add to the tail of the linked list. Then we also have get first. This will return the first element in the list. It's not going to remove it, just tell us what the element is. The element is the information stored in the node. Then get last also will tell us the last element. Then remove first will give us option to remove the first node. The node that head point to it, will remove it. Also, we can remove last node. The add here means to add an item into the linked list. Then we also have insert, but insert, you can see we have two arguments. We have the index and the object. So insert here gives us option and tell us where we should insert our item at. In the linked list, the first item is 0, the last item will be size -1. So insert gives us an option to insert an item at a specified index. Also, we have the clear. The clear will remove all the elements from the list. And also we can use contain. It will return true if the item we are looking for is inside. And then we also have get. Get also return the element from at the specified index. So get, let's say get 2, then need to go to the third position to get it. Also, we have index of. It will return the index of the first matching element. The index of takes an argument of an element. So anytime we see that element, is going to return the index of it. We also have a method to check if it's empty. We also have a method to check the last index and the get size, etc. Now let's look at the code now. This is the linked list and it's in the Python code. Going to zoom it more so it can be bigger. Okay. So here we can see our class linked list, as we said earlier. We end the name of the class with a column. This is object-oriented programming Python syntax. Then we have def for definition. Then this is our special, always in object-oriented, we start with the init or initializer. Then we know the linked list need a head, tail, and the variable for the size. So this will be our initializer or say constructor. Now the next method is to get first. So to get first means we want to check the first item in the linked list. So first, of course, we want to check and make sure there's at least one node in the linked list. So we said if self.size equal to 0, then return none, which means if the size is 0, there's no node in the linked list. So there's nothing we can return none. Other than that, we are going to return the head element. Same thing with the get last. We said that if the linked list is empty, return none. Otherwise, return the tail. The tail element will be the last node data. Then we also had first. Now, to add an element or to insert an element into a linked list, first, again, this is dynamic implementation. So the first thing we need to do is to create a node. So here you can see that we are using the node class now. So we should have the node class in this program or in this class, linked list class. So we create our node class first. Then after we are going to set first. So we are inserting, we want the head pointer to point to the node that we are inserting. So that's why here we say self.head. We assign it to the new node we create .next. Then the new node, we assign it to self.head. Here we say the head point to the new node. Then after that, we finish, but we have to increment the size variable by 1 to insert. Now, if the self.tail equal to null, it means the new node is the only node in the list. So if we have only one node in the list, then the head and tail must point to only that one node. So here we assign self.head assigned to self.tail. So that's our hard first to hard. Now hard last also is the same as hard first, but this time we are going to hard at the end. So first step again, create your new node using the node class. We are harding at the end. So you can see here, we assign the none to self.tail. Then we say the new node, we assign it to self.tail and then self.head. If only there's only one node in the list. So if there's only one node, first I assign the none to the tail, and also I have to assign the head also. Because if it's only one node, as the previous, the head and tail will point to only that node. Other than that, that means we have more than one node. So we assign the new node to the tail.next. Then the tail.next will be assigned to tail. So we just move the tail one more step since it's a new node. Then we increment the size also. Then next we can also do hard last. Now to hard last year is the same as hard. So anytime we call the hard here, it's going to hard at the last. But hard first is different from hard. Now to insert is the same as hard, but this time we are not harding at first and last, but we can hard between anywhere. So you can see here, first of all, we need to check where the index is. Here we say that if index is 0, it means there's no node in the linked list. So I have to do what? Do hard first. We don't have no other options. So hard first. Else, if the index is greater than greater than or equal to self.size, then we are going to hard last because we reach the end. We hard last. So depends on index. If the index is 0, means there's nothing, we hard first. If the index is greater than the size, that means we have to hard in the next. Other than that, we can hard anywhere. So here we assign the head to current. Remember, if I'm going to hard in the middle, I need to move a pointer to the middle. I don't want to use the head pointer, otherwise I'm going to lose my previous. So this current pointer is already created. So we assign the head to the current to create it. Then now we can move for I in range 1 to index. The index is where we want to move to. So if I want to move to index 3, then 1 to 3. If it's 20, 1 to 20. If we haven't reached there, now we are using the pointer current.next assigned to current. So what we are doing, we are moving the current pointer to the position we want to add. Then when we reach there, we put the node, we assign the current.next to temp, then we assign the node, the specified node that we want to the current.next. Then we assign current.next to temp. So now we assign the temp to current.next.next. Move one step. So we finish, then we increment the size by 1. Now to remove an item means we have to delete it. So first thing we check, if there's nothing in the linked list, there's no node, then return none. We can't delete anything. Other than that, we can delete this method, remove the head. So remove first, we are deleting from the beginning. So if that is the case, we assign self.head to temp. Then we assign self.head.next. We are moving one step. You see, now we want to delete the first item. We don't need to create a pointer no more. So when we use the pointer to move head.next to head, means we move the pointer to the next. That means the first node will be deleted automatically. So here we reduce the size by 1. Then we assign the none to the head. This means if the head is none, it means now after we delete finish, there's nothing no more. First of all, we check if it's empty. If it's empty, we return none. If it's not empty, then we move the head one step. Now, if we move the head one step, and now the head is none, it means now there's nothing no more. So both will be none. Other than that, we'll return the temp.element, that's returning the deleted element. Same thing, we can remove last. So here we say that, first of all, we have to check if the linked list is empty. If it's empty, we return none. Otherwise, if the size is equal to 1, which means we have only one item, that's it. We assign self.head to temp. Then we assign none to self.tail and assign to self.head. Then we change the size to 0. This is if there's only one item. We remove it. Other than that, we assign the head to current. Now we need a new pointer to move to the last item. So we say if I in range self to size -2, we move the current until we reach there. Now when we reach the end, we assign the tail to temp. Then we assign the current to tail, which is the pointer we reach. Then we assign none to tail.next to remove it. Then we increment the size by 1 and then return the temp.element. So this will allow us again to remove the last element. We can also remove at, which means we have to specify the index where we want to remove. So remove at is one argument, the index you want to remove. So first of all, we check if the index that is given to us is less than 0 or greater than size, that means it's out of range. So we return none. Now, if the index is 0, it means we just remove first. We saw the remove, we already written the remove first method. That means there's only one item. Then we reduce the size. Then if we want to remove last, the last else, return dot remove last to remove. Other than that, we can use the for loop again to go through. Now we are creating a new pointer named previous. Then we use the for loop to move through and reach the position we want to remove. Then we'll remove it and then decrement the size. We can also check if the linked list is empty. So this will return true if self.size equal to 0, which means it's empty. Now, if I want to get the size, I will just return the size variable. Size tell me how many nodes are in the linked list. And also we have a special string variable. This variable basically will represent and the string representation of the object that will create the linked list. And also we have a method to clear. So clear means we are going to remove everything. So we assign none to the tail and to the head to clear everything. Also, we can check if we have an item in the linked list. So this will then true if the list contains element O. So contains self E, implementation left as an exercise. So the rest, I'm going to leave this as an exercise or maybe make another video and we shall go through it. So again, after we create our linked list class in a different file, we can also create, this will be our main method. So first we import the linked list class. This is how we create our linked list. So our object linked list is LST. Now we can perform any method associated with linked list class. So first we click hard, we had America, then we print it, we insert Canada at the beginning, then we also had Russia, then we had we had the last node France, we insert, and then later we can also remove remove at 0 means we are removing the first item. Then remove at 2 means the third item, etc. Again, we are going to have another lectures which will focus on the coding section and some lab work. So we saw the implement at first. Again, the same steps here. Normally we can look at the diagram. So if I want to implement at first, the first thing I do, I create a new node. When I create a new node, I assign the next to it. The head will point to the new node. Then let's start the next will point to the previous first node. So this is hard first. And we can see the code here. Create a new node. Then assign the head to the new node next. Then assign the new node to the head. Increment the size. Now, if the tail equal to null, it means we have only one node. Then we can also assign the head to the tail. In this diagram, we didn't assign the head to the tail because we have more than one node. The same thing applied to hard last. We went through this already. Hard also is the same as hard last. We had and remove first also. We are going to remove the first item in the linked list. Then remove last, we remove the last item in the linked list. With linked list, everything is on the pointers. We have to do pointers operations. And remove at. Now the time complexity for list and linked list is almost the same except the three. So for example, to check for the index, list is more quicker because in array, we can just specify that we are going to index 2, index 3. So it's only one comparison, one task. But for linked list, we have to do the get index. So it depends on the size of the linked list. So n represents the size of the number of nodes we have. The same thing applies to insert. Insert for list takes longer, depends on the size. But hard first, I'll just hard in the beginning. Hard remove first, I'll just remove only one task. So there's a method here that we can use to compare linked list and the list using the start time or the time method. This method comes with Python. So here we create a linked list and also a list array and a linked list. We have the same range of data, 100,000. This is 100,000. We insert Chicago, the same thing. Now here we want to set, when we run this, it will give us the time it takes. So the elapsed time will be the time of the computer and the start time. And it to tell us how long. So this code is basically to tell us how fast list and linked list, their time complexity. And we shall come to the topic of complexity or time complexity. So the next will be the circular linked list. In the circular linked list, it's the same as a single linked list. The difference is that instead of the last node to point to none, the last node will point to the first node. So that's why it's like a circle, a circular list. So we say circular list is a single linked list, except that the pointer of the last node point back to the first node. So all the operations are the same. Also with the double linked list, now instead of having only one address for each node, which will point to the next node, we're also going to have the address of the previous node. So for example, with node 1, the first node, its previous node always will be null, nothing. and the next means is point to the next node. So node 2 have the address of the next node, which is called next, then also have the address of the previous node. So this means in our simple or single linked list, we only go one direction, but with double linked list, we can go opposite direction since we know the address of the previous node. So here we say a double linked list contains the node with 2 pointers, one point to the next node and the other point to the previous node. These 2 pointers are conveniently called the forward pointer and also the backward pointer. So a double linked list can be transverse forward or backward. So this example of a double linked list, we can see each the arrows can go forward or back, opposite. Then we saw the circular double linked list. So we have a double linked list, but also circular. So each node have 2 addresses, previous and the next. But again, the last next node will point to the first node. And next we talk about iterators. As we said earlier, iterators is part of object-oriented programming concepts. And normally iterator is an object that provide a uniform way for transversing the element in a container object. So we can record that we can use for loop to transverse element in a list or a tuple or a set or a dictionary and a string also. Again, we went through list, tuple, set, dictionary. We can use the for loop. So this is an example here using a set. We create set 1. You have 4, 5, 1, 9. Now we say we are using for loop. So we say for E in set 1. If each element is greater than 3, then we print it. So this will give us, we'll print 4, 5, 9 for us. We have the print. So here we are using the for loop to go through the element. At the same time, we can also use iterator. So here we say, can you use a for loop to transvert element in a linked list? No. To enable the transversal using for loop in a container object, the container class must implement the iterator. Remember, this is just a set. So we can use the for loop, as we said, we can use the for loop to go through items in a list, such as array or a tuple or a set or dictionary. Example here is for a set. But with linked list, we cannot. So can you use a for loop to transverse element in a linked list? No. To enable the transversal using a for loop in a container object, the container class must implement iterator. And this is the name, the method iterator that will return an iterator. And this is iterator, return the linked list iterator head. So then every iterator have a special method called the next method. The next method make it possible to move to the next element or next object in the container. So here we say an iterator class must contain the next method that return the next element in the container object as shown in line. Again, this code is in our textbook, chapter 18, figure 18.2. And we have it here. So this is our linked list class again. So I won't go through this. And one thing I forget to mention, you will see that we have the class node in the linked list. Then this is what we created now. We need a linked list iterator. So this is our linked list, class linked list. This linked list iterator will make it possible to transverse through objects in a linked list container. So here we have the initializer. This is the special method next, which make it possible to move to the next element. And that's it. So this is, with this iterator, we can be able to transverse through there. So always, if we want to transverse, we have to create a linked list iterator object. It can be any name, but the type will be linked list iterator, which automatically we have the initializer to initialize the object, and also you have the next method, which is very important to transverse. So the code is here. we can see we assign the self.current.element to element, then current.next to current, which make it for us to move to the next. And there's an example here of a Fibonacci program. And so again, we are going to have a lab work here. We focus more on the theory here. So that will be the conclusion of this lecture. So again, these lectures, we cover Python programming language for linked lists. In our next lectures, we are going to cover the stack, queue, and priority queue data structure using Python. Again, thank you for your time.